Thank you. Good morning. It's my pleasure to be here, and I certainly think this is a topic which is deep into my historical background and my experience, both in the research as well as in the education part, and I think it's good to learn something from the experience that I have acquired over the years. Let me outline a little bit the main ideas, main items that I would like to address. Is first of all, I would like to explain the increasing role of mathematics in innovations for circuits, systems, and signal processing. Probably I do not have to dwell too long on this item. I think the majority of this audience, I would expect that they are already convinced about it. Then another issue that I would like to raise is the long trajectory to become a professional or a researcher in signal processing. If you look at your own history, and including mine, you would see that there's a trajectory that you have from primary school, secondary school, university, and then the research activities and the education activities, the teaching. So there are several critical steps, and I would like to address certain critical steps, and we can learn something from some experiences and some evolutions. Also, I would like to explain that there's kind of dynamical forces or evolutions and impact on research and education. The mathematical methodologies that are needed for signal and image processing, for classification, data fusion, biomedical diagnostics, support vector machines, matrix and tensor decompositions. I will give some examples from our research and also explain a little bit the ways of thinking about it. Cryptographic algorithms I would like to address also, because we started in 1982 already a group working on cryptography, not the military, but or the diplomatic cryptography, but the open public scrutiny developed cryptography, which is needed, of course, more and more in our modern society. And we can learn important lessons. I would like to draw attention also on the issue of reproducibility. Reproducibility of research and the reproducibility of research in research reports in signal processing is an interesting topic. To show that I have a little bit of a background, I made my PhD with Professor De Wilde, and he made his PhD with two supervisors. So this is the mathematics genealogy. You can look at it on the web, and if you look at my name, you will find that I had about 43 PhD students. I didn't put these on below because I didn't have enough space, but I put some others that were preceding me as my grandfathers and things like that, even going back to Plücker, Gauss, Euler, Lagrange, Poisson, Fourier, so it's Lipschitz, all names that we have learned. Somehow I can consider to be a little bit an inheritant, a little bit. I should remain modest, of course, but it's nice to know it, of course. Okay. The increasing role of mathematics in innovations, the explosion of computing power, and it's likely not to be finished yet. The digitalization, Internet of Everything, smartphones, digital cameras, social networks, electronic payment, big data. In our group, several people are working hard on big data also, distributed energy production, and also the societal challenges, security, privacy, safety, permanent education, healthcare, green energy, climate change, environment, and aging, care for the aging populations. So there's evolutions and there's challenges and there's interesting opportunities. These are some pictures about it. You can easily recognize. I will not spend the time. The biomedical signal processing, it must be very well known here that there's essential elements of signal processing, parameter estimations, and improved diagnosis based on measurements, and there's signal processing, biomedical signal processing is quite crucial. Opportunities, I mentioned already. I will not, the pictures say more than the words, I think, here. The data, medical data. Medical data, if you look at the size of a CD-ROM, 750 megabyte, and you see that with all the data that can be collected, biomedical data, the PACS is a university clinic information system. The petabyte is, 1 petabyte is 10 to the 15. So it's, you see that there's an evolution that is still growing about data, and to handle all these data, there's a lot of processing, and signal processing can have interesting contributions there too. Community detection, it used to be in the past more trade networks, but telecommunication, biological interactions, and social media, again, interesting opportunities for mathematical issues. With this background, I would like now to show you a special report that has been made on the perception of the relevance of science and technology by children at the age of 15. It's the famous ROSE study. It's already 4 years old, but I think it's still, as far as I'm concerned, still a very actual, a very useful report that you can download from the web. And if you haven't heard about it, I think it's worth looking at it. What do we see in all of these diagrams? I will show about 10 of these diagrams. You see the countries listed. Typically, the countries here on top are typically in Africa and less developed countries, India, Philippines, and so on. And if you go into Europe, you see somewhere Poland also. Like, let's take Poland here. And for Poland, you see here on this line a scale of from 0 to 100. I would like to have as much as possible science at school. And for Poland, we see that it is here somewhere between close to 40. If you look at other countries in Western Europe, it's even less. And there's a distinction between men, female, and male students. The male students are the blue, so they have more interest typically than the girls. So somehow this gives us already a perception that the interest in having more science in the less developed countries is much more present than in our countries. And somehow I think this is a sign that is not so pleasant and not so good. There's more specific questions. What is your interest in knowing how plants grow and reproduce? Also, you see the same countries have a rather low interest with respect to the other countries, the top countries. Oh, sorry. Chemicals, properties, their properties and how they react. Again, there's a difference. The boys are a little bit more interested in it here than the girls, but still in our countries it is not as well developed. Detergents, soaps, how they work. Here the girls are a little bit more interested than the boys, but still it's rather low. The interest in the lives of famous scientists. The boys, it's here, this one, oops. Famous scientists, yes. Is it? Oh, I have more space on my.
In the center laser.
Okay, in the central laser. Okay, good, thank you. So, the laser.
Yes, it works.
I should
Just switch it on.
Okay, good. Okay, good. Thank you. Right and left. So the interest in the lives of famous scientists, I showed my genealogy. For boys is rather low, and for girls it's even lower. I would like to have we had this one. Okay. if you look at purely technical questions, the way how computers work, boys are interested in most of the countries, but girls are much less interested in it. And if you look at a quite technical issue, how do petrol and diesel engines work, the boys are interested in it, but the girls are definitely not interested in it. So you see there's a lot of interesting lessons to be learned for the age of 15. That's the age before they make a decision what type of studies they will engage. But somehow we learn from this that probably we have a problem. What to eat to keep healthy and fit, the girls are more interested in it than the boys, and the girls are really strongly interested, and the boys medium interest. And people should care more about the protection of the environment. Everybody is interested in it. The boys a little bit less, but still. And can you influence what happens in the environment? Then you see some discrepancies in the top countries here, the top of the list, of course, but certain countries have the feeling that they have less influence on it. And definitely here the boys are less motivated, while the girls are more convinced that they can personally influence this issue of the environment. And certainly when you ask the question, is science, technology, can they solve all the environmental problems? You see that the countries in Africa and Asia are very much convinced about that, whereas in Europe it is rather low. So we see that we observe that the students do not choose careers in STEM, science, technology, engineering, and mathematics. And would like to get a job in technology. For the boys, there's more willingness to become engineers, but the girls, and typically in our country, we have around 15% of female students in engineering. And the numbers are not increasing, not really decreasing also, but this is a very stable number, and it's amazing. In contrast to all the efforts that are being done for it, it doesn't work. For becoming a scientist, it's rather low in these countries also. So we learn from this that we have to address the social relevance of science and technology and make it clear to our young people before they enter the higher education system that there's really opportunities for having a life and activities in their life where they can really make the difference to the societal problems and, for example, the environmental problems. So we need to solve it or to tackle it in the secondary education. And the important issue is, and we are now in the process in Belgium or in Flanders, to include some STEM programs and STEM courses in high school already, where they bring together the 4 components of science, technology, engineering, and mathematics, also in the more classical education programs. So they can take, for example, still Latin and combine this with STEM. So there's experiments on the way, and there's also a plan to implement this. So this is a way to really make sure that the students already at the young age are aware of the fact that these 4 have many links with each other. There's interdisciplinarity. Every problem that is posed in society has very strong aspects of science, technology, engineering, and mathematics. And the mathematics should not be left out. The mathematics is not a single pillar that is remote from society. That's the issue, and that's what I wanted to say here. So the link between mathematics and daily life should be stressed more. So this is a bit of publicity. It's a book that we published last May. It's in Dutch, of course, because we want to address high school students and their teachers. And this is a book which is called The X Factor. The title is chosen by my younger colleague. I was not aware about X Factor and all these things that are known by younger people. But basically, a girl with a high X Factor is a girl to which you look a little bit longer than you would normally look to another girl. So we feel that mathematics is also in a similar position. If you look a little bit longer to the mathematics than normally, superficially, you will see that there's so many nice things, so many important things, so many attractive things in it that you want to spend more time on it. So what do we do in this book? We have, in fact, 20 stories. It's not a book with mathematical formula. It's a book with stories. Stories about daily life, stories about the industrial floor, stories about the future of man on Earth. In total 20. I haven't written 10, my younger colleague has written 10 too, and we bring them together. But my style was a bit more old-fashioned than my younger colleague. So somehow the publisher said, well, we perceive a little bit of difference in your styles. Of course, I cannot deny it. I have a classical style of Latin and writing text with many arguments and long sentences. The publisher wanted to have an attractive book for younger people. So it has been converted. My younger colleague has converted my parts into his style. I must say that, acknowledge that. He is very much motivated, but I think it's good to tell that these books now, we already sold about 1,100 of the 1,600 that were produced, and somehow we see that there's probably need for a second edition. It's about the stories, like one of the stories I wrote was about online banking. Probably also in Poland, everybody is doing more by online banking rather than going to the bank itself. But if you do the online banking, there's several steps in it that you have to do in this process. And these steps are really needed to convince yourself and also the bank that this is a transaction that you want to pay 50 euros or 50 zlotys to this person and not to another person and not a different amount. So somehow, to guarantee all these elements, you have deeper mathematical questions. So the mathematics is inside, but is not revealed to the public as such. But on the other hand, if you are a student and if you're a teacher and you're teaching about number theory, and you can use some of these examples in your lectures, saying, look, when you do this step, you typically use some number theoretic issue or property here for this. That's why what we do in this book. So probably if you have a need for such a book in Polish, there's an opportunity we can discuss. So this is a little effort that we did in the past year because we are convinced that it is important to bring these messages. So the trajectory that I mentioned, many stages, built over many years, primary school, secondary school, university. Another thing that we should think is that mathematics is different from the physical sciences. In the physical sciences, you had the classical mechanics, the relativity theory, quantum mechanics. Each time you have a new type of paradigm. The old one is somewhat bypassed. So somehow you restart. In mathematics, nothing is wrong if it is proven to be correct. And always new branches are growing. And the tree of mathematics is a tree that is getting larger and larger. And somehow we as engineers, and I will explain a little bit if I have time enough, that we as engineers are there to see which fruits are there for us to use in our work in signal processing. So if you're creative, you can say, I look for mathematical methods on this tree, and maybe you can help to build a branch, to make a branch a bit stronger, because that branch, by the mathematicians, they are not so well aware about the applications. The branch need to be some extensions with new theorems that are more suited to the practical needs that you have. And of course, also the mathematics is inside is also an important issue that we should counter. Okay, first thing that I would like to spend some time on, let me check on the timing that I do not spend too much time on, is the transition from secondary to higher education. This is a little story about our experience in the Flemish country, the Flemish part of the country, about the story of how this has evolved. We had a long tradition in Flanders, together with our French part of the country. Adam already mentioned that we have two regions, the Flemish and the French, that were together, had the same education program for a long time. And then we had, for more than 100 years, you have an entrance examination of mathematics for engineering. During my young ages as a professor, I was also involved in this entrance examination for the subject of analytic geometry, where you bring algebra and geometry together. So we are asking questions about cones and about lines and curves. And so it was a nice exam, which was important for testing the skills of the students before they enter engineering. And this was an exam which was an entrance examination, so if you fail, you could not start engineering. Typically, we had about 70% of our students succeeded in the exam, and typically 70% of our students succeed in the first year. So the net result is that we have about 50% success in the whole procedure. When in the Flemish part and the French part there was autonomy for education, education is a subject which is related to the culture of the people, so it was regionalized. The Flemish government had the autonomy, and they decided, the politicians, that they should abolish this entrance examination because there were not enough engineers. So open the doors, you will have more engineers. What was the result? We get 20% more students that begin. I was teaching 12 years ago, subject of linear algebra, same as Adam, in this university for 550 students. But we had 20% more students, but we failed 20% more students in the exam. So the net result is that we again had the same amount of students in the second year, and it was no gain at all. This was not on purpose, but because you have to accept more students, you inevitably, and you want to have the same standards, the same level at the end of the first year, we had a little problem there. So I took the initiative, and I was supported very much by the dean at that time in 2013 to set up some position tests. It's not against the law to offer a test which students can freely participate. Not mandatory, not binding. So everybody can participate in it, and you get the results, but you get additional information. And that's what we wanted to play on. So it's not an entrance examination. We call it a positioning test to position the students with respect to their peer group. And it's not to orient students, because we assume that these are already students that have the intention to start engineering. And it is held 3 months before the start of the year, so typically it's held at the end of June, when the high school is finishing. We do the test. One day, or one afternoon, or one morning, 30 questions, multiple choice, and they get a set of formulas. We do not test how they can memorize formulas, but we test how they can solve problems. So we offer them a problem. A boy and a girl are racing with a bike from A to B, and when do they meet, and this type of things you can easily imagine. I can show you some more details if you're interested in. These are typically 30 multiple choice questions, which are a little bit trying to see whether they can apply the formulas that they have learned in high school. They're in the top part in the high school education in mathematics, and we test them and we score them. Our ambition was to have 60% succeeded in the test. So this part, this should be the threshold for succeeding. If we divide the total population into 5 groups of 20%, the upper 20%, the next 20, and the third, so these 60%, we call that they could succeed in the test. We encourage them to proceed with the studies. Those who have failed not so badly, we try to stimulate them to make some extra effort, because we feel you still might have the potential. And those who badly fail, we try to discourage them from starting. But we cannot forbid them, because the law is saying that every student, democracy, every student can start the studies. This is a bit of Dutch, but I will try to explain what the impact is on the choice of the study program. Basically, we have 3 steps here. The test is in July, end of June, beginning of July. We have a second test in September, and we have the start of the year at this point. So if you look at the stream for 1 year in 2015, 633 students participated in one of the 2 tests, and 75 students did not participate in any test. It's not mandatory. But you see, we only have a small part that entered the studies. Only 14% did not take a test at all. So in that sense, we really catch the majority of our potential students. What happens with them? Of course, they do the test in July. Some succeed, that's green. If they do not succeed, it's red. For those who succeed, you see that 82% start the studies. Some already take the exam when they are in the last but 1 year in high school, before they really. Some, if they fail, they can do the test still in September. And if they then succeed, 92.8% start with the studies. For those who fail the first time and do not repeat the test, you see that only 25% start with the studies. So it has a discouraging effect for those who do the test in July. For those who do the test in September, you see that 55% still start the studies. So it's too late to do a test just a few weeks before the academic year starts. That's what we learn. But normally we are bound to organize 2 sessions. 2 options for the students is kind of the rule for all the exams that we organize. You can also ask the question, what happens with these students when they enter into the first year? How do they succeed in the first year? It's a bit difficult to explain, but the rough lines are that we distinguish 4 groups. Black group is those who stop with the studies. Red is those who have so many subjects that they fail, that they will not succeed in the first year. The green ones are the ones who have almost no failures, or some failures that can be still tolerated. And the orange is a bit in between red and green, of course. So if you look at the participants of the test, if they have more than 14 out of 20, so the best ones, 60% are green. And you see that the other ones are very small. If it's between 10 and 13, 31% is green, and there's an orange part which is quite dominant, 41%. Red is already 21%. So our test is not perfect, but we do not measure the whole performance of a student. We measure only the mathematics, and there's more to the succeeding the first year than the mathematics, of course. If you look at those who had less than 10, you see that 42% will not succeed in their first year, and 22% dropped out. And interestingly enough, with such an experiment, you can see what happened with those who did not participate in the tests. If those who did not participate in the test have a pattern which is very similar to those who failed the tests. So somehow we are sure that we have with our participation, we have the students that really have a good chance. And so what we do at our university is all those who either fail the test or do not participate in the test, they have to do additional mathematics tests in the first year. So they need special care, and the other ones are exempt from that. So somehow we see the positive role, and we consider this the kind of coaching that we try to do, because our goal is to have more engineers on the work floor. That's what our government wants. There's also a whole trajectory to guide the students towards this positioning test in high school. There's an orientation phase and information phase, but once they have a clear choice at the end of June, they have a clear choice, most of the students, we do the test. We confirm, we question, or we dissuade the students. Once they started, we monitor the activities and support them and coach them and observe and maybe reorient still, but hopefully not too many have to be reoriented because they waste a year. The future is that there's no need to make it mandatory, we feel, but our minister has the plan that's now. She knows about our program and she wants to implement it in a mandatory way. Already other subjects than engineering have the similar test. We have here about 1,800 participants in 2015, and in September a little bit less. So we have a team of professors from the different universities in Flanders to set up the questions. I'm the chairman of this committee, and we meet 2-3 times per year to set up this program. It's a nice program, and I am convinced that it serves a useful purpose. Okay, coming now to the general trends in education. In general, it's my feeling, and also our country is no exception, that the mathematics skills in many countries in Europe are still strong, but have a tendency to slow down. The populations of engineering and the gender unbalance I already mentioned. The bachelor-master program is implemented in most countries. I heard here that you have a 3.5 years bachelor and 1.5 years master. We have a 3 and 2, so but that's not very essentially different. The evolution of the students, we observe that our students have less patience and they want instant gratification. They want to see much faster than the former students what they get for what effort that they make. Our program in engineering is now, I was also involved in the setting up for this program. We have 1.5 years for all engineering students together, and then we choose a major and a minor. So for example, here you could combine, you have as well civil engineering, construction engineering as electrical and computer science, and then for the next 3 semesters, computer science and electrical engineering can be combined, or mechanical engineering and electrical engineering. And then for the master program, we have, of course, electrical engineering in a master program, but also biomedical engineering, energy engineering, and we have also a subject, master in mathematical engineering, because we consider that the mathematics in our program as it used to be when I was a student and as it was some 20 years ago or 10 years ago, that mathematics has been reduced in the bachelor. And this reduction is now taken up by having a specific mathematical engineering that the students can choose after the bachelor, where they go deeper into methods like the optimization methods, more advanced optimization methods, more cryptography, also mathematical techniques of cryptography are in there and things like that. This is a slide which I've taken from a presentation that Martin Wetterli gave at USIPCO on mathematics in signal processing. Applications change, computing platforms change, students change, and the challenge of an educator is to see that knowledge is growing. Time in school does not grow. If you look at most countries, I heard here also that the number of hours, contact hours with students is reduced over the past years. Must be willing to call details to convey the big picture. Should teach what is most reusable and generalizable. So these are nice recommendations. This is a slide which I included because I think it opens up some new way of thinking, the way which mathematics can be taught. 2 elements in it. Steven Strogatz has written about the mathematics, a pleasant article about mathematics in the New York Times, a sequence. Interesting to read and to see that there's really interesting ideas that live and that younger people should be more aware of it. The second one here is called street fighting mathematics. Mathematics should be fun, and by extension I would say also the mathematics of signal processing in circuits and systems should also be fun. What do they do in this book? They use some shortcuts. Typically, we are used to teaching mathematics by having definitions, theorems, proofs of theorems, new definitions, new theorems, new consequences, and you build up a structure step by step in a long procedure. This way of doing street fighting mathematics is saying here the art of educated guessing and opportunistic problem solving. So they use different methods. Here you see the list of methodologies that they use: dimensional analysis, easy cases, lumping, picture proofs, not the type of written out proofs, but picture proofs, successive approximation, and reasoning by analogy. By the way, this book is freely downloadable. It's about 90 pages, and there's an introduction by Carver Mead. And one of the ideas is that our brain is more developed visually than symbolically. So somehow, if you can use this symbolic or the visual aids, then you can gain. I don't have so much time to explain here, but one example which I find remarkable is the proof of the fact that the algebraic mean is greater than or equal to the geometric mean, which is the square root of a times b, for positive numbers. If time permits, I can give this proof, but it's a nice one. A is here and b is here, so if you put the two together, you see that we have a diameter of a circle here with diameter a plus b. And so at the transition from A to B, we have here an orthogonal line, and here we have a rectangular triangle with an angle that is 90 degrees. And now we have the property that this triangle and this triangle, that they are proportional. So we can say x over a x over a is like b over x. So this is something with basic geometry that they learn in high school, still at our place. You can easily derive the formula x squared is equal to ab, and that's basically saying that this x, this length, is basically the geometric mean. So you see on the picture here, you see already that the geometric mean, x, and the algebraic mean, which is the radius, that they are different, and that the radius is always larger than the geometric mean. And you can also see that when a is equal to b, then they're both equal, and when b is smaller, much smaller than a, that there will be a bigger difference. So you have a better feeling on the relationship between geometric and algebraic means, which can be useful also in fields like signal processing. So nice and interesting. I recommend you to read the book, and now I get a little bit closer to signal processing and circuits and systems. Circuits and systems, and or rather in a central location, typically in engineering education, also at our place, I presume here too, between the mathematics, the physics, and other subjects that surround it. So it's a central role, and it has a bit an abstract nature, but still very important, and also important for the future. What topics should be dealt with, and I would like to stress here, Laplace transform, Fourier transform is an important topics, and the fact that you have to be careful when you have Laplace and Fourier transform. Substitution of S by j omega does not work for many signals like sine, Dirac, step. That's an issue that I was always discussing with my students. Also, the initial conditions for the Laplace transform. There's an interesting paper in IEEE Control Systems magazine on the issue of this 0, 0 minus, or 0 plus for the Laplace transform. Interesting. I feel this is important also in a good program on electrical engineering and steady state behavior versus effect of initial conditions. And of course computers, but computers do not substitute thinking. I think we should still have good insights. There's a whole discussion also on having discrete time first and afterwards continuous time, or the other way around. Historically, the way I was educated was, of course, continuous time, and we had very little on discrete time, only in the last year a little bit. This has, of course, been turned upside down in many places, and I also prefer to start with discrete time. It's a better link with algebra, and you don't have the problem with the Dirac impulses, which are quite unnatural. When students first hear about the Dirac impulse, this is not something they can say, I go to a shop and I buy a piece of equipment that will produce a Dirac impulse. It will not, the shopkeeper will say, well, where did you study? What kind of stupid ideas did you get in your school? So somehow discrete time is a bit easier. This is a shortcut for the transfer function that I used already in my first year course on algebra already. I will not dwell on it, but basically they know already the complex exponential. And if you have a difference equation like this one, and you have an input which is a complex exponential, in fact it is the real part is the cosine, of course. And if you then assume that your solution, your steady state solution, is of that nature also, and you substitute, then you can see that this h, the transfer function, is obtained here. And there you can see the most important concept in all of I would say, signal processing and system theory is the notion of a transfer function. So understanding that this transfer function is something which turns out with a little bit of algebra in a very quick way and is crucial to understanding the behavior of many different systems, also in signal processing. So the discussion, continuous time versus discrete time, is still going on as far as I hear and see. Somehow I feel that there's benefits to both. So somehow a pragmatic approach where you do the things that are more natural, more easy in discrete time, and the things that are more easy in continuous time, and try to combine it in such a way that it attracts the students is probably the best way to do. Okay, some elements on research. I have to watch my clock. I will give a few examples, but I will do it in a very sketchy way. The mathematics you see here, the signal processing and the applications. What I would like to stress with this diagram is that it's my feeling that the mathematics has many nice things to offer to signal processing, which at the same time can have direct impact on applications. On the other hand, the applications can make you think about certain signal processing algorithms that need further development of mathematics. So somehow it's a kind of interaction, which is always a two-way interaction, not just a pure thing that some people have a model in mind. First, the mathematicians develop something, then the signal processing guys will develop something, and then it will be applied. I do not believe in this model as the exclusive model. I think there's a two-way interaction because we can learn a lot from applications. For example, data fusion or signal fusion is an interesting application side which has impact on signal processing, but also on the mathematics behind it. So, the misconceptions, all mathematics is already discovered. No, that's far from true. Many young people think that, and so somehow the teaching is brought in such a way that it is giving the impression, oh, all the mathematics is already developed. No, no. All useful mathematics is known to the signal processing community is also not true. The signal processing community has to wait until the mathematicians have proven their theorems. Also, this is not the way I think about it. This is a joke, of course. If you have a rotation, I think, Adam, you can use this in your lectures. Some students have, of course, some misconceptions, and I wanted to include this not to wake you up in case you are a bit asleep. Signals, processing of signals, we worked a lot on singular value decomposition and signal separation, and I will typically, these are measurements taken from a lady who was pregnant and with electrodes that are placed on her body at different places. And typically, when you measure the electrical activity, you see that there are spikes, and typically these are originating from the electrical activities of the muscles inside the body. If the lady is asked not to breathe and not to move with her arms, the only muscles that are active are the heart of the, we hope that the fetus is not moving, that the electrical activity of the heart, of the mother, and of the fetus. If you look at it, you see some smaller spikes at a different rate in some of the recordings. Of course, this you do not present to a medical doctor or to a gynecologist. A medical doctor or a gynecologist would like to see only the fetal ECG. So what you want to do is you want to apply linear algebra to these signals. You apply linear combinations to these signals in which way so that you can eliminate the mother ECG, and that you can show as much as possible the fetal ECG. So that's a kind of, we have looked at the mathematics, and if you work on it, I will not go into all the details, you can derive some equations for making linear combinations on the signal matrix. The signal matrix is typically this matrix here. To my students, at the first year, I tell, this is a matrix. It's a matrix of 6 rows and 1,600 columns. To explain to them that this is the way engineers will encounter matrices. Not the matrices that come from the sky, but that come from reality. So, and then you can make linear combinations in directions that bring you certain values. And then you use singular value decomposition, but since I'm sure you are all aware here of the singular value decomposition, you can use that in order to find the most dominant components. And typically here, you have 3 components which are dominant for the mother ECG, and the 4th component is the component that is due to the fetal ECG. You can also use a slightly different concept, which is the ratio of oriented energy, where you have 2 sets. If you have a set of a matrix A that contains good versus a matrix that contains bad signals, you can apply a ratio of oriented energy. And for that, there's a mathematics developed for a generalized signal value decomposition where you have 2 matrices and where you have 2 decompositions which are linked to each other. I will not spend the time because I want to still continue with some more examples. The next step which we have taken is, because matrices are typically sets of numbers with a number of rows and a number of columns, but in many applications you have not only rows and columns, but you have a 3rd dimension or maybe a 4th dimension. So you have really a block of data, and these are called typically tensors, and this can be due to the fact that you have a sequence of images, or you have some color images or things like that. And can you apply also mathematics to that? Yes, we have developed some higher order singular value decomposition for arbitrary tensors. This is a rather weird way because such a tensor, A is a tensor, the script and the S is also a tensor, and you use our orthogonal matrices that transform the A into a part which is like the central part in the singular value decomposition, but it contains all the information about the energy in the tensor. So it's a compact way to represent the energy elements. How can you compute that? By unfolding the tensor, by cutting it according to horizontal, vertical, or tangential directions, and doing regular singular value decomposition. The computation I will not spend time here to save some time. And here you see already that we have the regular singular value decomposition, the generalized singular value decomposition if you have good and bad signals. And if you have tensors, you can also have one tensor and apply the higher order singular value decomposition. And if you have 2 tensors, a good and a bad one, you can have the generalized higher order singular value decomposition. So we see that we can have, typically this is something that mathematicians would not come about, but which we felt from signal processing applications that was a need to develop. Signal separation is an important topic in signal processing. I mentioned at the beginning also that we teach our students a lot on optimization in the mathematical engineering program. Typically, we had a project with across all different departments, from chemical engineering, mechanical engineering, electrical and computer science, where we were all working together in developing methods for doing not so much the classical optimization where you have an optimization algorithm, but rather for optimization engineer from a good insight in the mathematics of problems that are raised in practical circumstances, and a good insight in convex optimization, where you can really deal with huge and largely huge data sets and with the potential that is much more than with the regular optimization methods. We can have better solutions. This requires not just to formulate a problem here and then push it onto the software, but rather to manipulate the problem until it has a convex version, a convex equivalent or a convex near equivalent that can be solved very efficiently. Because convex optimization is really the fast way for solving optimization problems. Other optimization problems tend to have the difficulty that there's many local minima and you can hide, you can miss certain, if you have a proper reformulation, you can have a rather nice, of course this is only shown here for a two-dimensional case. Typically this is for high-dimensional cases also. That's the role of mathematics, to go beyond what you have visually here. So, interesting convex optimization. We apply also some of these methods to prediction of electricity load. Here you see a diagram of 52 weeks of a year, and here you see the hours of the day from Thursday to Wednesday. You see that during the weekend the energy consumption is lower, and the vertical direction you see the amount of energy that is consumed. Such diagrams help in order to predict the future consumption. Combining electroencephalogram and functional MRI with our younger colleague, Professor Sylvine Van Uffel, there's PhD work going on in collaboration with the university clinic to combine this information. Here also we need this type of tensor decompositions. We have also convex optimization, I mentioned already. Regularized regression, if you have data and you fit it with polynomials that are too high order, then you see that you obtain an approximation which is bad. You should do it with lower order. Support vector machines, with Johan Suikens we have a nice development which is called the least squares support vector machine, which is used a lot and has received a lot of citations. Typically, if you have a support vector machine, a regular support vector machine is, or a regular discrimination between the blue and the yellow dots, the separating line that is having a maximal margin will touch at the boundaries of this open region the number of support vectors. Of course, this is for a problem that is linearly separable. Many problems in practice do not tend to be linearly separable. So in that sense, your problem is more likely to be something like this. And through the kernel trick and the least square support vector machine, you can develop a conversion from the application domain that you have here into an abstract, higher dimensional space where the problem is linearly separable, and then you can convert it into the original space, and you see that this is the separating line among these two sets. Very interesting, least square support vector machine has been applied to many, many applications. We have the software also. The PhD students put the software, open source software, available. If you have interest, you can use it. I certainly wanted to say, I'm sorry about the delay, I will make it quick. Cryptography is important in our society. Historically, military and diplomatic research on cryptography was dominant. This was secret research, secret algorithms, and secret keys. Everything was secret. So nothing for universities to enjoy, because you're not supposed to do any of these things. So somehow we felt already in 1982 that there is a need for more open research. And for example, electronic bank transfers and electronic payment systems, open reproducible research ask for different ways, where you have standards, open and reproducible research, open algorithms. You do not hide your algorithms. If you're strong enough, you can say, my algorithm is known. That's called Kerckhoffs's principle. The only thing you keep secret, and you have to keep secret, is, of course, the keys. You do not throw the keys like for your house. You do not put your keys available for the thieves. We started a group in 1982. I was the head of this group initially, but now we have 5 faculty and about 22 postdocs and 40 PhDs. And actually one of the big successes was the advanced encryption standard, which was designed by 2 of my former PhD students, Johan Rijmen and Vincent Damen. Johan Rijmen and Vincent Damen, yes. And this was also described in the Wall Street Journal. Actually, I was very happy to see that at your city of Poznan, there's a statue that has been set up. Actually, I visited this yesterday afternoon to make sure, and I see there's a nice exhibition about this, about a fantastic work that was done by the 3 Polish cryptographers, which was a bit not recognized very well in France and Germany, and definitely not in Germany, but also in England, but now has become a recognized important contribution that has shortened the Second World War. In fact, also IEEE has recognized this with a milestone award. Cryptography, here I will not spend the time just to avoid getting too much delay. The last thing maybe on reproducibility of research. I feel that the reproducibility of what you do in signal processing should be good. In other words, if you publish a paper, you should make your data available, you should make your algorithms available, and the reviewers can then use this to check if they want to, and also the new researchers that start can already use this in order to make progress. So progress in society will be better. And it will avoid malpractices, which is one of the things that certainly we should try to avoid. And actually there has been a study in the IEEE transactions on signal processing. Actually, I must say my son was doing this study with Martin Vetterli. He was checking all the papers that have appeared in 2 years in the signal processing transactions, and these were evaluated for their reproducibility, and they were also evaluated for their number of citations. And you see that the papers that were not reproducible and that were reproducible, the last 3 here for 2004, 5, 6, that they have better averages of citations, because if it's reproducible, more people will use it and more people will give reference to it. So somehow it's an encouragement to do that, and if everybody does that, I think we have a good situation. This is some of the group that I was heading when I was before my retirement. Now I keep myself with other things. So recommendations, good practices for teachers using geometric interpretations, examples, historical facts, and open problems. Many challenges still, but I mentioned most of this. I think I can conclude here because I do not want to abuse too much of the time. Thank you.